Let's take a look at some familiar objects. When I move among these objects, there is no change in the position of these objects. That's because these objects are at rest. Now let's see what happens when these objects move. Wow! Did you see how fast the car zoomed away? The ball has also disappeared out of sight. The globe shows how the Earth rotates on its axis. But the rocking chair is still here. Its movement looks very inviting. I'd like to relax in this chair. So, what changed around me? The objects that were at rest started moving or were in motion. Motion can be of various types. It can be regular and controlled, like in a watch, or erratic and uncontrolled, like that displayed by the tsunami that took thousands of lives. Now, how far do you think the car will go? How long will the globe take to rotate completely on its axis? You can obtain answers to such questions through the study of motion in physics. These answers will help you control motion and harness it for constructive purposes, like in a hydroelectric dam.
In this lesson, you will learn about motion and related quantities. At the end of this lesson, you will be able to define motion, identify instances of motion encountered in our everyday life, analyze motion along a straight line, identify uniform and non-uniform motion, calculate speed and average speed, define velocity, calculate velocity of a moving object, explain scalar and vector quantities, define acceleration and calculate acceleration of a moving object. In everyday life, you see some objects at rest and others in motion. Birds fly, horses gallop, water flows through rivers, and cars move. You say these are in motion. Thus, motion is a state of an object in which there is a change in its position with respect to its surroundings and time. When a car race starts, the position of each car participating in the race changes relative to the stands, spectators, and so on. This is because the cars are in a state of motion. Tiny particles such as atoms and molecules and heavenly bodies such as planets, stars, and galaxies are all in motion. For example, Earth rotates around its own axis and revolves around the Sun in an orbit. Similarly, other planets, solar systems, and galaxies in the universe are all constantly in motion. None of the moving objects that we have looked at exist in isolation. They may have other moving or stationary objects in their environment. What happens when we compare the state of two or more than two objects? For instance, let us consider the state of a car driver. Is he at rest or in motion? It is difficult to answer this question. This is because, with respect to the car, the driver is at rest. But with respect to the other things around, he is in motion. Thus, the states of rest and motion of bodies are relative. Absolute states of rest or motion do not exist. Consider a bus moving along a road. A passenger in the bus perceives the trees and other objects outside the bus to be moving, while his co-passengers seem to be at rest. Similarly, we cannot see the rotation or evolution of the Earth. However, based on the changes in the environment, at various times of the day and transition of seasons, we can infer that the Earth is rotating on its axis as well as revolving around the Sun. Hence, overall, you are in motion as a part of Earth, but at the same time, you are at rest with respect to your immediate surroundings. Motion of objects or bodies can be one-dimensional or linear, two-dimensional, or three-dimensional. One-dimensional or linear motion involves an object moving along a straight line or in a specified direction. For example, cars moving along a straight path in the circuit exhibit linear motion. In two-dimensional motion, in a given plane, an object moves in two directions at the same time. For example, a golf ball, when hit, flies off making a large parabolic path over the golf course. It travels in two dimensions or directions at the same time, horizontal and vertical. If we observe an airplane taking off from a runway, it ascends rapidly in one direction and after gaining some height, turns towards its flight path. This type of motion, where an object moves in three directions at the same time, is called three-dimensional motion. In this lesson, we will cover motion along a linear path in detail. You can measure the magnitude of movement of an object using two quantities, distance and displacement.
Hi, I am called displacement. I will always show you the shortest distance between the initial and final points, or the aerial distance between 2 points. My cousin is called distance. We often look similar, so it can be a little confusing for people at times. However, there is a unique feature that sets me apart from my cousin: my sense of direction. In fact, because of this characteristic, I always display a special bold letter or an arrow on my head.
Let's look at these quantities using an example. At the end of her school day, Mary goes from the school to the playground. The school is 3 kilometers away from her home and the playground is 4 kilometers away from the school. So, from home to school to the playground, Mary travels a total of 7 kilometers. This is the distance travelled by Mary. Thus, distance is the actual length of the path covered by a moving object irrespective of the direction of motion. However, the straight route from Mary's home to the playground is only about 5 kilometers long. Therefore, Mary's displacement from home to the playground is 5 kilometers, as against the distance covered by Mary in reaching the playground, which was 7 kilometers. Thus, displacement is the shortest distance between 2 points irrespective of the path between the points. When an object is in motion, its motion may or may not be consistent all through its journey until it comes to rest again. Let us observe the yellow car in the race. What do we see? The car moves 50 meters every second continuously. Thus, for each second, if we note down how far the car has moved from the starting line, we see that the displacement during any 2 consecutive seconds is the same. This car is in uniform motion. An object is said to be in uniform motion if it shows equal displacements in equal intervals of time, however small these intervals may be. Now let us observe the red car in the race and record how far it has moved from the starting line for each second of motion. We see that its displacement during any 2 consecutive seconds is not the same. This is non-uniform motion. An object is said to be in non-uniform motion if it travels unequal distances in equal intervals of time, or equal distances in unequal intervals of time. Different objects may take different amounts of time to cover a given distance. How fast does a moving object change its position? The answer to this question relates motion to the time taken for the change of position, and that brings us to speed. Speed of an object is the rate at which an object covers a given distance or changes its position. Speed is calculated as a ratio of distance covered to the time taken to cover that distance. Thus, an object that covers a relatively large distance in a short amount of time is moving at a high speed. Conversely, a slow-moving object has a low speed and covers a relatively small amount of distance in a relatively longer duration. An object at rest has no speed. Speed is measured in centimeters per second in the CGS system and as meters per second in the SI system. Typically, you measure speed in kilometers per hour. 1 kilometer per hour equals 5 divided by 18 meters per second. Or 1 meter per second equals 3.6 kilometers per hour. Let's try applying this formula to one of the situations we reviewed earlier. In our previous example, Mary's school is 3 kilometers away from her home and the playground is 4 kilometers away from the school. If Mary walks to school from home in 20 minutes, her speed can be calculated as 3000 divided by 1200, which is 2.5 meters per second or 9 kilometers per hour. However, generally, the motion of an object is not uniform from its starting point to its final destination. Its speed varies at different points or stretches in the journey. In such cases, to determine the speed at which the object covers the total distance, you may need to gather data on the speed of the object at each instant when it is in motion, and then calculate the average of all these instantaneous speeds. However, gathering so much of data can be tedious, and certainly impossible in the case of large distances. Therefore, we typically use a quantity called average speed in our calculations. The average speed of an object is the ratio of the total distance covered by the object to the total time taken by it for covering that distance. Like motion, speed can be uniform or non-uniform. Thus, an object in uniform motion has uniform speed, and an object in non-uniform motion has non-uniform speed. If you rearrange the formula for speed, you can determine the distance covered in a given period of time at a given speed. S is equal to d divided by t. Therefore, d is equal to s multiplied by t. However, it does not give you the displacement of the object. To determine the displacement of an object, you need to know the direction of motion, along with the rate of the motion. Velocity is the speed of an object moving in a definite direction. Velocity of an object is defined as the rate of change in the position of a body. It can also be defined as the rate of displacement of an object. Velocity is calculated as the ratio of displacement of the object to the time interval taken for that displacement. Velocity is measured as centimeter per second in the CGS system and meter per second in the SI system. Similar to speed, velocity is also measured in kilometers per hour. Velocity of an object can change by either changing its speed in a particular direction or by keeping the speed constant and changing the direction. When the yellow car takes a turn and moves ahead, its velocity becomes variable. Like average speed, you can calculate the average velocity of an object having non-uniform motion. Average velocity is defined as the ratio of the total displacement to the total time taken. When a body is moving with variable velocity for t total time duration, u and v are the magnitudes of its initial and final velocities, during which it has a total displacement, that is, s total. The average velocity of the body is the average of u and v. That is, it is half the sum of initial and final velocities.
Hi, can you make out the change in the velocity of my hands as they work round the clock to tell you the time? The tip of each hand moves with uniform speed but changes direction continuously as it moves in a circular path. Thus, if you consider the second's hand, its velocity actually changes each second. When the second's hand completes one full rotation in 1 minute, it comes back to its original position. At this point, its displacement becomes zero, and hence the average velocity also becomes zero.
So far, we have reviewed some related measures of motion, that is, distance and displacement, and speed and velocity. Among these measures, distance and speed have only magnitude, whereas displacement and velocity have magnitude as well as direction. A physical quantity that has only magnitude but no direction is scalar. Length, area, distance and speed are all scalar quantities. On the other hand, a physical quantity that has both magnitude and direction is vector. A vector such as displacement is simply a scalar with direction. Let's look at a car in the race. A yellow car is currently at a distance of 7 kilometers from the starting line. However, if we measure the straight line from the starting line to the position of the yellow car, the car is positioned at a point just 5 kilometers towards the northeast direction. Here, distance of 7 kilometers is scalar, whereas the displacement of 5 kilometers towards the northeast is a vector. For an object in non-uniform motion, its velocity may change with time. Rate of change of velocity is expressed in terms of acceleration. Thus, if a body moves in such a way that its velocity changes, then it is said to be accelerating. Observe the car moving swiftly in the circuit. When it approaches the turn, it slows down and after negotiating the turn, quickly gains velocity again. This change in velocity of the car is known as its acceleration. Acceleration is the ratio of the difference of final and initial velocity to the time interval during which the velocity has changed. Acceleration is a vector quantity and is measured as centimeter per second square in the CGS system and as meter per second square in the SI system. Like speed and velocity, the acceleration of an object can be uniform or non-uniform. A freely falling body gains velocity due to gravitational forces at a uniform rate. Thus, it shows uniform acceleration. However, a car negotiating a turn shows non-uniform acceleration because its velocity changes at a non-uniform rate. When an object moves such that its final velocity is less than its initial velocity, it is said to possess negative acceleration or retardation. Here, the two buses A and B are moving along a straight path. The bus A is gaining velocity, hence it is accelerating, whereas the bus B is losing velocity, and hence it is retarding. For example, Consider a bus traveling with a velocity of 20 meters per second. The bus comes to a halt at a bus stop over 5 seconds. In this case, the acceleration of the bus is -4 meters per second square. Thus, we say the retardation of the bus is equal to 4 meters per second square. To summarize, let's take another look at the relationships between the quantities we just studied. Distance represents the extent or length of motion. When distance is mentioned with the direction, you get displacement. A change in distance with respect to time gives you speed of motion. Similarly, the rate of change of displacement gives you velocity. When you measure the change in velocity with respect to time, you get acceleration.